Have you ever wondered how your brain knows which way something is moving, while your eyes and entire world are in constant motion too? Welcome back to DeepVisus, where vision meets depth. In this episode, we unpack Chapter 8 of Stephen Grossberg's Conscious Mind, Resonant Brain, and tackle our guiding question. How does the brain see and recognize object motion without losing track of where we are or what everything else is doing? Let's start with a crucial design choice of evolution: parallel visual streams. The what stream, also called the form pathway, delivers razor-sharp orientation and binocular depth. The where stream, the motion pathway, delivers precise direction and speed. Trying to do both jobs in a single circuit would cancel critical information, so the brain runs two specialized processors side by side. Think dual core vision. Inside the motion stream, the brain applies two filters that work back to back. One, short-range directional filter, pulls brief, local signals to amplify reliable edge terminators, tiny features that flag real motion cues. Two, long-range directional filter, sweeps across space with elongated Gaussian pooling to build true direction-selective cells and launch traveling G-waves, neural ripples that stitch together widely separated motion signals. These explain classic illusions like long-range apparent motion, the Turnus display, and the delta phi effect. Those filters feed a layered circuit Grossberg calls FORMOTION, short for 3D form and motion. Here's the essence. Transient and sustained inputs merge. Competing directions battle it out. Winning signals climb to area MT for object motion and area MST for higher order feedback. That top-down feedback acts like an art resonance, amplifying motion directions that fit the global pattern, suppressing those that don't. In real time, it solves the notorious global aperture problem: how the brain chooses the correct direction when each local piece of edge is ambiguous. Now add attention. The same feedback loop that unifies motion signals also carries volitional directional priming. When you expect motion to the right, a priming pulse zooms down the pathway, biasing the competition before the stimulus even appears. Grossberg shows this is why attention can sweep long or short distances in nearly equal time. The G-waves carry it like a neural surfboard, and we can't ignore navigation. A complementary stream, MT plus to MST, adds optic flow vectors to pinpoint our own heading, while the MT to MST loop subtracts vectors to track external movers. Together, they form ViSTARs, vision for self-trajectories and responsive steering. In plain language, avoid collisions, follow targets, and keep your path straight, all at once. So, let's answer our opening question. Your brain sees object motion by splitting labor into two visual cores, layering short-range and long-range evidence, and closing a resonant feedback loop that merges automatic capture with conscious attention. The result? A seamless, stable movie of the world, even while you and everything in it are constantly in motion. If these neural G-waves have sparked your imagination, stay sharp. Next time on DeepVisus, we'll push further into Grossberg's framework and explore how the brain fuses vision with other senses to build a coherent self in space. Until then, keep your eyes open, your mind curious, and remember, DeepVisus, where vision meets depth.